Okay, so in this section we'll be talking about chemical reactivity and mechanisms, but a lot of it's going to be on whether reactions are going to be spontaneous or non-spontaneous, and if they're spontaneous, how quickly they'll proceed. So we'll do some kinetics as well. So first let's look at bonds and remember what our bonds are. Let me get here. If we've got an electron that's in a non-bonding orbital here, and we have an electron over here that's in a non-bonding orbital, we'll just make this hydrogen. Why not? Each of them has one electron. Down here, when we draw the molecular orbitals, this is our bonding orbital. Oops. My pencil did funny. So those two electrons, when we get into bonding, move into a lower energy state. And then up here we've got an empty non-bonding. So bonds form to provide a lower energy state. So it just makes sense that you're going to have to input energy to break bonds anytime you break a bond. And one more thing about before we leave bonds, bonds can be broken heterolytically, where here we have X and Y, and both electrons move to Y. We designate that with a double-headed arrow. The base of the arrow always starts on a source of electrons, so it starts here on that bond. We can also have bonds broken homolytically. And here we have, we've got X and Y, and we've got two fish hooks. One electron goes this way and the other electron goes that way. That's a homolytic bond, and we'll be looking at homolytic bonds later in later chapters. But right now, all the ones we've looked at are heterolytic. Okay, so the two things we'll be looking at here is enthalpy and entropy. So first we'll look at enthalpy. Enthalpy, with enthalpy we've got endothermic and exothermic. So endothermic reactions, the delta H will be positive and energy is absorbed from the surroundings. An example of one of these reactions is one of those cold compresses. You break the little bubble inside and you hold onto it and it gets cold. Sometimes sports teams have them. But this is a reaction that as you touch it will be cold. If we draw the energy diagram for that reaction, we have the value of H on that axis, and this is the reaction coordinates. We're going to just abbreviate there. Reaction coordinates. We have a starting energy that's here and a product energy that's here. So this is our reactants and this is our products, and the energy reaction curve looks somewhere like this, and our delta H is this distance here. The difference in the energy of the reactants and the products. Okay, so if we go to exothermic reactions, the delta H is going to be negative. Energy is released. So if you burn wood, that's exothermic. It releases energy. If we draw we're going to be drawing a lot of these reaction diagrams. Here we've got H on this axis and reaction coordinates over here. Our reactants have higher energy than our products. And our curve is going to look something like that. We'll do red this time because the energy is released. So the delta H is going to be this distance here, and it's negative because it falls. We can predict the sign and magnitude of delta H by using a table of known delta H's. So this little knot symbol means that the reaction is measured under standard conditions, and we can take our broken bonds and subtract off our formed bonds, and that will give us the delta H. Now, remember, broken is energy that's going into the reaction, and so it's positive. We subtract the formed bonds because they're being made, and this is energy that's going out. So let's look at our first example. First, we need to figure out which bonds are being made and which ones are being broken. So in our reactants, it looks like there's hydrogens, of course, here that aren't normally drawn. And we have broken one of these hydrogen bonds. So I'm going to mark that. This bond right here is broken. We also have to, if we're going to make this hydrogen bromide compound, we're going to have to break this bond right here. So those are our broken bonds. And we can go to our table and find those bonds. So we've broken a bromine-bromine bond, and that is, I should have looked this up ahead of time. Here it is, 193. And the other bond that we've broken, this is a carbon that's bound to two carbons. My goodness, what did I do there? This is a carbon hydrogen bond. This carbon is bound to two other carbons. So we need to look on our table for a carbon hydrogen bond that has this format. So here's a carbon that's bound to two carbons, and then it's bound to X. There's the hydrogen. So this is our 397. So these are the bonds that are broken. Oops. 397, and that's going to be plus 193. Now we're going to subtract off the bonds that are made. This carbon-bromine bond is made, and this hydrogen-bromine bond is made. We go back to our table. We're looking for a carbon that's bound to two other carbons and then something else. So this would be our number right here. And we're looking for a bromine-hydrogen bond, which would be right here. And let's go back back to black. I think black's easier to see. So we have 285 plus 368. And that will give us a minus. And this, I believe, is in kilojoules per mole. Okay, now let's look at another one. This would be a good idea for you to stop the tape right here and make sure you're getting the right numbers. Okay, so this is a carbon. It's attached to 3 carbons and a chlorine. So the number for this is 331. Oh, I'm sorry. I didn't mark which bonds were broken. So let's do that. We're going to have to break this bond, and we're going to make the carbon-oxygen bond here. Now, we're going to have to make this bond, the hydrogen chloride bond, and we're really going to need to rewrite our water so that we can see the bonds. So the bond that's getting broken here is a hydrogen-oxygen bond. And there is a special enthalpy for that. It's 498. It's on the table. And then we're going to subtract off 381 plus 431, and that will give us, a positive 17. So you need to practice, make sure that you can find the right bond on the table is really the only trick for this. And remembering naturally that the energy that you use to break the bonds is positive and the energy that's used to make the bonds is negative. That's energy that's lost